Okay, all right, we are back and we're going to go ahead and get started with Stephanie. How do you say your last name?
Ribet, like
Ribet?
frog.
Oh, Ribet. Okay, love it. Okay, so Stephanie's just come. Were you over at the Molecular Foundry today, or did you work over there?
I'm a staff scientist at the Molecular Foundry.
Okay, cool. Oh, wonderful. Okay, so just down the road over there from the lab. So, all right. Well, thanks so much. And Stephanie's I'm actually very excited about this talk. But I'm an accelerator physicist, so I love this stuff. So, all right, take it away. Thanks.
Cool. Thank you. And everyone can hear me okay? And I hope people on Zoom will like yell at people in the room if they can't. Okay, so as I said, I'm Stephanie, and I work over at the National Center for Electron Microscopy, which is part of the Molecular Foundry here at the lab. And the techniques and the tools that we work on is scanning transmission electron microscopy, which is a way of allowing us to directly image things down to the atomic length scale, which is where the title of my talk comes from. And my overall theme today and what I want to talk about is how including computation and all kinds of computational imaging in our workflow allows us to do things and image things that we couldn't otherwise understand. So I'm a material scientist. So before I really talk about electron microscopy, I wanted to emphasize the need for this, and really the main theme that we have that goes across material science is the importance of nanoscale. And this includes when we're thinking about interfaces that are on the nanoscale, so materials like energy storage materials. It turns out that if you look at really their nanoscale interfaces, that's what drives performance, as well as materials that are intrinsically on the nanoscale, like nanoparticles are really good for recovering pollutants, critical materials recovery because of their small size, large surface area to volume, and very tunable chemistry. This idea of smaller length scales also plays a role in applications like quantum devices, where we have confinement, where we get these unusual physics that arise. And then also when we think about designing things that meet nature and the structures and the length scales that occur in nature. So this is a COVID spike protein, and designing a vaccine, thinking about different sort of medicine that might interface with this. We think a lot on the nanoscale. So the overall theme is kind of often in material science, when we're thinking about these different types of problems, we want to understand and develop materials that are on this sort of small length scale. And the tool that I use is really ideal for addressing this sort of critical length scale. It's a scanning transmission electron microscope. In our STEM microscope, depending on how we align the beam, we have a very small probe. This can be on the order of a few nanometers to really a sub-angstrom beam, and you can collect all kinds of different signals at the same time. You can do imaging, which tells you about the morphology of your sample. So for example, here you can see titanium is grown on graphene and the shape that this adopts. You can do diffraction, which gives you really local information about the structure and the ordering. So we can probe different phases. We can see transitions from crystalline to amorphous regions, get really local structural information. You can do spectroscopy, which tells you all about composition and bonding that's in your material. And then lastly, we can do this in situ. So you introduce external stimuli like heating, biasing, cooling, light, and watch how materials change. So for example, here you can see these different gold nanoparticles that are growing together. And the dots that you're observing on this screen, these are actually columns of atoms. So this is what I mean, we're doing atomic resolution imaging. We're imaging where the atoms are in this material. So the purposes of the presentation today, I wanted to start by thinking a little bit about when does STEM really work and what are some examples of where this excels. So I pulled some data from some recent experiments. This is an ongoing collaboration with the ALS where we're using both X-ray and electron microscopy data to understand ordering in both crystalline and amorphous materials. And these are gold nanorods. And you can see it's a dark field STEM image that I've false colored by the orientation of them. And you can see hopefully on this screen some sort of preferred alignment. And this is due to the self-assembly in these materials. I would consider this a relatively low magnification image. And STEM is really great for being able to see how these nanoparticles align and assemble due to the polymers that are connecting them. Another example of when STEM works very well, these are collaborators at UC Davis who grow these thin films of metal oxides. You may have heard about graphene and magic twist angles and sort of interesting properties that emerge. Instead of these conventional 2D materials, we're looking at these metal oxides. STEM gives us a way to directly probe the twist angle in these materials. You can see we're transitioning from a single layer to a double layer region. And these dots here again are columns of atoms. So we're getting at very high resolution an understanding of structural changes when these metal oxides get stacked on top of each other. And my last example is, again, more towards metals. This is a medium entropy alloy, so many metals mixed together. This is a thermoelectric material, and we wanted to understand the performance of it. And when we put it in the stem, you can see these needle-like rods growing here. This is something that would have been very difficult to probe with other techniques. And here STEM again provides direct imaging and visualization of the structure that we've grown. The next question is, where do things go wrong? What is there still to do? There's many answers to this question, but one big problem that we have in microscopy is damage. So this is a carbon nanotube. This is a material composed of light elements. It's very weakly bonded, and after repeated exposure with the electron beam, you can see breakdown of this carbon nanotube and really defects forming. And we want to image something in its pristine state, not its defective state. So we keep this in mind all the time when we're operating the electron microscope. Another challenge we have is contrast. So these are nanoparticles grown at the Foundry. I cropped it and zoomed in and took this image. Still very excited to get this atomic contrast, but what happened when I overlaid my structure is you can't see the fluorine atoms. It's very hard to see light, weakly scattering elements. And this can be solved with computational approaches, and I'm going to be talking about that in my talk today. And then the last issue I wanted to talk about is not just an electron microscopy problem. It happens in all kinds of different imaging modes, and it's a projection issue. So if you look at this picture here, you are looking at two giraffes, but it looks like a giraffe with two heads. And this is because you're just looking from one viewpoint. And we have the same problem in STEM. It's inherently a projection technique, and a lot of 3D information gets lost in translation. So if I go back to this previous micrograph I showed you before, this is titanium on graphene. We don't know our titanium graphene. We don't know if it's titanium on graphene, graphene on titanium, or some layered structure where they're sort of sandwiched in between. If you're developing a microelectronic device, you want to know the answer to that question. So you need to move beyond just this conventional imaging. So this is what my talk is about, is how can we do better? And this is really what we work on NSEM. And I have kind of three parts of the talk. First, I'm going to very briefly talk about hardware and specifically cryo-electron microscopy. The main part of my talk is about software, so different types of approaches we can use for reconstructing data to get better images. And then in the end, I'm going to talk about experiments and specifically about automation and data pipelines, specifically as related to NERSC. So I'll start by talking about the hardware part of this, and specifically cryo-electron microscopy. So cryo-electron microscopy has been pretty revolutionary in the field of biological sciences for solving structures of proteins. And a big part of this is when you cool samples down, you can minimize damage and you can take better data. And you can see a big change, a big step in what's called the resolution revolution in structural biology, moving from what was called blobology, so you just have a loose idea of what these proteins look like, to really actually being able to solve them down to the angstrom length scale, or the atomic length scale. And increasingly, we're recognizing this value in material science as well. We're cooling samples down, slowing down damage to get better quality data. The second thing you can do with cryo-electron microscopy is studying quantum transitions. So cooling samples down either to liquid nitrogen or liquid helium levels and be able to probe very subtle structural changes. Now, the reason that this is important and the reason that I wanted to bring this up at the beginning of my talk is you may or may not know, but there is a new microscopy center coming to Berkeley lab next year. This is CryoEpic. It's going in this new building right here that you might have seen coming into the lab. This is building 92. This is going to be a joint project between the molecular foundry and the biosciences. And we have 3 new tools coming to the lab as soon as early next year. So the question that I ask myself all the time, which now I'm asking you, is if you were thinking about setting up this center, and the thing, as you'll see in the rest of my talk, computational imaging is very important for low dose, as is cryo-electron microscopy. What sort of hardware and software pipelines would we need? And more importantly, what can we start developing now? So this is sort of the hardware part of the only hardware part I wanted to discuss today. And if anyone's interested in discussing this later, I'd be very happy to. So now I'm going to move into talking about the software, really how does this computational imaging work? There's lots of ways you can generate a lot of data really fast in the microscope, but the flavor I'm going to talk about is 4D STEM. So in our conventional electron microscopy experiments, you have your probe, and as you scan across your sample, electrons are scattered, and they fall on these bright field and dark field detectors. And for every position in real space, you get just one value. You're integrating all the signal that goes there, and a lot of scattering information is lost. So now, thanks to hardware developments, we can now collect full diffraction patterns at each position in real space. This is called 4D STEM. So you have two dimensions in real space, 2 dimensions in reciprocal space, and you get what's very position sensitive diffraction information. So now you can see kind of probe very small structural changes on the nano to atomic scale. This is great, but as we know, 4-dimensional data is not very human digestible without doing a certain amount of work. And that's what I'm going to be talking about now. To give you a sense about the amount of data I'm talking about, we have cameras that run very fast. So we're talking about 400 gigabits per second. Depending on the type of experiment, what you're looking at, these scans can be as big as about 100 gigabytes uncompressed in memory. So this means users are not actually processing their data on laptops. We're moving towards workstations or people are processing the data here at NERSC. And then depending on how you count, there's about 8 microscopes that are on their way to NSEM, in NSEM currently being installed that can do these different types of experiments. Users, depending on the user, can collect up to hundreds of scans per day. And another thing that's important when thinking about workflows is all of these microscopes are developed by different vendors, have cameras developed by yet other different vendors. So these workflows are not exactly portable without doing a little extra legwork. So that's something we think about. I'm going to give you 2 examples of 4D STEM and show you how these workflows actually, what we're actually doing. And my first example of the value of 4D STEM is all about plastics and development and design of plastics, especially from recycling. So we know that plastics, when they get recycled, they end up in these mixed waste streams. If you take plastics and melt them down and try and reform them into something, you sometimes run into trouble. So for example, polyethylene and polypropylene, these are 2 very common plastics. If you melt them and reform them, you get something with very poor mechanical properties. And this is well understood. This is because these plastics phase segregate and they get pulled apart. So they just don't have very good structural properties anymore. I'm working with some researchers at UNC and Berkeley lab who have introduced a cross-linking agent. This is a small amount of chemical you can add, which changes the bonding. And now we can get something with far superior mechanical properties. So the question they were asking is, can we understand what's going on? We think this is some sort of structural change on the nanoscale. And can we do this with electron microscopy? Before I tell you, kind of show you the example of the value of computational imaging, let's take a look at what it looks like with conventional approaches. So what we do conventionally is something called stained TEM, and you can compare here between, you see the polypropylene and the polyethylene, and just like I said, these materials phase segregate. If you compare this to the crosslink case now, you see a very different type of morphology, but this doesn't really quantitatively tell you what's going on. It just gives you an idea that these structures are different. The other thing you can do is X-ray scattering experiments, which tells you in the bulk what the structure is. It tells you that you have polyethylene and polypropylene, but we weren't getting position-sensitive information. Enter 4D STEM, we can actually get this sort of information now. So in these semi-crystalline polymers where you have crystalline domain, you can get diffraction, and we can actually probe this. So 4D STEM is quite versatile. So we can reconstruct this 4-dimensional data in multiple different ways. This includes reconstructing images. So this is very akin to sort of the conventional images you saw before. But we can also make maps of where the crystalline domains are and also their orientation. So for example, for polypropylene, we can make a map that looks like this. These lines represent the crystalline domains and the color represents their orientation as well as the lines. We can do this for polyethylene as well. You can see that there's quite large grains in this field of view. It's mostly dominated by a few grains. And this is quite different now if we compare this to the crosslink case. In the crosslink case, we have a very strong preferred alignment in the polypropylene. We have much smaller grains, they're broken apart. And we also see that we have alignment beyond the interface. So this cross-linking agent isn't just affecting the polyethylene-polypropylene interactions, but really just modifying this polymer more generally. The other way you can plot this data is like this. So here now red is polypropylene, blue and purple are the different polyethylene reflections, and we have the not cross-linked and the cross-linked case. And you can see these structures are very, very different from each other. And this sort of computational imaging approach allows us to collect a lot of information. In the case of the cross-linked sample, we can actually start to make a map of how these different crystalline domains interact with each other and what we think is actually happening at the interface. So the overall takeaway here is that these 4D STEM approaches allow us to get orientation information that really isn't accessible with conventional imaging approaches. And to underscore this even further, let me remind you of what a conventional imaging approach looks like. You see the morphology, you see the structure, but you have no idea what the crystals are actually doing in your material. 4D STEM lets us probe this. So for today's talk, I also want to tell you a little bit about how this works. So this is what our raw data looks like, very noisy, but we do a lot of pre-processing. So binning, aligning, calibrating, applying polar transforms, symmetry operations, and we get something with sufficient signal to noise that we can do this detection. This allows us to figure out where our reflections are, and we can turn this into a scattering profile and use this to isolate in reciprocal space where these reflections are and make maps. These processes are currently run on CPU on workstations or NERSC. They take approximately 10 minutes. For similar processes, we've made a lot of headway with speeding these up by moving to a multi-CPU framework with something like Empire or GPU-based programs. And so that's certainly something on the horizon for this particular workflow as well, especially as we think about incorporating this in something like streaming, which I'll talk about later. So I'm going to switch gears and talk about a different way to process 4D STEM data now. For the microscopists in the room, this means aligning your microscope a little bit different, getting to higher resolution. And for the data scientist, this means running now a much more complicated algorithm. These are GPU-enabled workflows. These are iterative algorithms where we're solving for the phase of our sample. And the way these two methods are called parallax and tychography. And basically what we're trying to do is solve the phase of our sample. In an electron microscopy experiment, we have some incident beam. This is complex. Our sample has a complex transmission function. It creates a complex exit wave. And our detectors do not record the phase. We only record the intensity. And this is not just an electron microscopy specific problem. It plagues lots of different fields. If we are able to recover the phase through these iterative algorithms, we can solve a lot of the problems I introduced at the beginning. We can do more dose-efficient characterization. We can image our weakly scattering signals. That means getting our light elements. And we also can even recover some 3D information, which is really great for a lot of samples. There's many flavors of this, but the basic idea of how this works is you have some initial guess for your probe and your sample. You have a forward model that allows you to compare your guess to your experimental data, and then a loss function helps you update your guess. And you're running this iteratively over and over and over again for your entire data set, and it can get quite large. So let me show you an example of why we'd want to do this. This is a project I'm doing with some researchers at UC Berkeley. We have 2D materials. We're ion irradiating them to form defects for applications like sensing and filtration. And we want to image atomic defects in this very weakly scattering material. This is what a conventional image looks like, even on a state-of-the-art microscope like we have at NSEM. You can see big defects, you can see where your lattice is, but it's very hard to see missing atoms, pick those out. If we move to a computational approach, to different field of view, same sample, you can see very clearly why we like these workflows that include this sort of iterative algorithm. We can get a much cleaner picture, and you can actually pick out where the atoms are in this position. So it's not just about running these iterative algorithms, it's about the way you actually do this. So our initial reconstruction looks something like this. These tychography methods are not just electron microscopy specific, but we spent a lot of time thinking about how to develop them, incorporating the physics of scattering that are electron microscopy specific. So we apply a bunch of constraints and calibrations. This is calibration optimization, position refinement based on kind of some known types of scan distortion we have on our electron microscope, some amplitude constraints based on calibration data we took on the microscope, and you get a much better reconstruction. This can be improved yet again by using mixed state. So this allows us to account for the partial coherence that's in our probe. And this is how we get to our final optimized reconstruction. So this is one way to run this algorithm and optimize it, but we've actually been moving to an even different framework for this as well that includes acceleration and some ML tools. So basically, we've moved to an auto differentiation framework, which makes our lives a lot easier. And we're also including some deep image priors in the loop, which provide a lot of benefits, including intrinsic denoising. So if we compare here, we have our stochastic gradient descent on the left. This is what we were doing before. Atom is allowing us to converge much more quickly, including our low spatial frequencies. And then we get some additional benefits by having this DIP in the loop. This is especially clear looking at this data. This is some MOF data, which is very topical if you're paying attention to today's Nobel Prize news. And this is data from the literature, and you can see how much better the reconstruction looks if you're using this sort of deep image prior method as well. So I just wanted to kind of end this section by saying, I've talked about the methods we use here, but we're really applying this across all kinds of different challenges in nanoscience. And this means the way we take the data is a little bit different day to day with different users, and also the way we reconstruct it. So recent samples that have been in our microscopes include qubits. We're looking at both amorphous and also crystalline components. Ferroelectric films, people want to come in and see small displacements in like oxygen positions, and we can probe that directly with tachographic reconstructions. All kinds of different battery materials. This was a sample I was most recently looking at earlier this week, where we're looking at structures lithiated and unlithiated and seeing how they change. We've done a lot of work looking at these photon upconverting nanoparticles that are grown and developed at the Foundry and seeing how defects correlate, including in 3D, with the performance of these materials. We even look at monolayer materials. So now you're actually looking at individual atoms, and you can pick out a few handful of missing atoms and understand how the structure changes very precisely when these are removed. And then also we've been applying the same code for looking at protein samples, which is yet a very different direction in terms of the experiment. So I hope I've convinced you the power of doing all these computational imaging approaches. And I want to talk a little bit about the experiments and the challenge we actually have in practically implementing this. So the overall problem statement is this: we have great microscopes at the Molecular Foundry. We take data very fast. We have lots of interesting samples, but the great compute resources that we want to use are here at NERSC. So how do you get the data from the Molecular Foundry to NERSC? Through a previous NESTAP proposal with Peter Ursius, Bjorn Enders, and Chris Harris, they've made a lot of progress in thinking about this, and specifically for the TEMO5 microscope. So on the TEMO5, we have a home-built 4D camera. It has 4 data receivers, and previously this was transferred by sort of a file I/O procedure in many steps. Instead, they've replaced this with now a streaming process, RAM to RAM. So now this data can get much more quickly to NERSC. And as Sam Wellborn, who's over here, has shown and spent a lot of time developing, we can do this much, much faster, get the data from NERSC to NSEM than we could before. So you can see how much better we do in terms of time for streaming versus file transfer. And this is really important for thinking about on-the-fly reconstructions. So now the next step is to go a bit further. So not just get the data to NERSC, but start to initialize some immediate reconstructions. So for example, here, this is a video from recent experiment Sam was doing, where you can see as the data is coming in, it's also getting live processed. And it's in this sort of interact-EM, very front-facing user interface. And this is important because a lot of times in the microscope, you're taking data such that you're taking it blindly. You can't see anything that's going on until it's processed. So if you do have a pipeline like this, now users can take data blindly, see what's going on, and reconstruct it on the fly. The last thing I wanted to talk about in terms of data collection is actually data pipelines is actually automation of the data collection. So like many people, we are fascinated with LLMs, and we've been testing this out and seeing how this might work in the electron microscope. So with our TEMO5 microscope, we've set up through MCP the ability for Claude to interact with it. So we have 4 MCP servers, a microscope server, a Crucible, which is a Molecular Foundry way for storing data and metadata, one that operates the 4D camera, and one that is Distiller, which is a platform developed here at NERSC for allowing users to transfer and process data directly. This automation has worked pretty well. So we can ask Claude now, for example, Claude, can you take a tomography tilt series for me? And it's pretty interesting to see what Claude does, but the answer is yes. It says, of course, I'll help you take a tomography tilt series. And it starts by doing some really smart things by figuring out what's currently going on in the microscope and acquiring images. And we're able to start to get these tilt series. This is pretty fun, but also pretty useful because a lot of these tomography experiments are very tedious, very time intensive. And you could imagine you could save a lot of mistakes and help users develop algorithms on the fly for this. We can do even better. So some of these methods I've been talking about, like parallax and tychography, require some experience and expertise for how to take the data. You operate the microscope a little bit in a funny way. So we said, hi, Claude, we want to do some of these tychography experiments. Here's some good scans. Can you give us some suggestions for parameters? And of course, Claude was happy to guide us step by step with recommended parameters for this experiment. And we ended up with a nice reconstruction in the end. So this was pretty cool. There's certainly more to do here, and we'll see, we'll all find out if LLMs are here to stay. But what's nice about this is it really builds upon some really central things we already had going on at NSEM. This includes writing low-level code to operate the microscope. The TMO5 is especially scriptable thanks to all the hard work of Peter Urshias for developing these methods to script the microscope, and also pipelines like Distiller and Crucible, where we're storing metadata and other information that these platforms can easily access. So in summary, I've told you about a lot of things today. I've told you about hardware, I've told you about software, and I've told you about experimentation. And this is very exciting. There's certainly more to do. Peter and I are very excited to be continuing with a new NESAP proposal. And kind of if I can give you an overall sense of what we want to work towards. The idea is we want people who come to Berkeley Lab to do experiments, not to spend 3 days on the microscope and leave with a stack of hard drives, a link to a GitHub repository with a handful of tutorials, and us to say, good luck. We want people to come to NSEM, to take data, to interact with it, get feedback, take the best data possible, and also walk away with hypotheses. You know, I wanted to do this experiment because I developed this material and it has this interesting property. And then I went and I looked in the microscope and I now see this defect I didn't see otherwise and start to generate hypothesis. And we have a lot of the puzzle pieces for making this happen. There's certainly more to do, but this is what we're going to be working on, and we're very excited. So I have many awesome collaborators to thank. None of this is done on its own. So I have also would really like to acknowledge, of course, the Molecular Foundry and NERSC, where a lot of this data collection and processing has been happening, and I'd be happy to take any questions. Okay, everyone's excited about electrons now. Totally clear.
Cool, thank you so much. Okay, great. There's Leon. I was like, oh, where's our next speaker? Okay, thanks so much, Stephanie.
Thank you.
You should be able to share. All right, great. All right, our next speaker is Leon Hostetler from IU. Yeah, and take it away. Thanks so much for being here.
Thank you. So my name is Leon Hostetler. I'm a SciDAC-funded postdoc at Indiana University. And today I'd like to talk about our work accelerating lattice QCD inversions using multigrid and deflation. So this is not just work that I did entirely on my own. The people listed on the slide here were very heavily involved. Of particular interest, I'd like to point out Kate Clark and Evan Weinberg. They were really some of the early developers of the multigrid algorithm that I'm using here. And they've now been at NVIDIA for quite some time, but they continue to be heavily involved with Lattice QCD and have helped a lot with this project. So I've benefited a lot from this kind of collaboration with these NVIDIA people. So I'll start by giving kind of an overview of the work we do in Lattice QCD. And I'll talk about one of the main computational problems that we face, which we call critical slowing down. And I'll present two possible ways of mitigating this. So eigenvector deflation and staggered multigrid. So quantum chromodynamics is the fundamental theory of the strong interaction. So that combined with the weak and electromagnetic interactions forms the standard model of particle physics. So QCD describes the interaction of quarks and gluons, and we need that in order to understand things like fundamental parameters of the standard model and hadron properties, nuclear structure and interactions, as well as high energy early universe physics and beyond standard model physics. So in many regimes, let me see if I can move this little thing that's bothering me. In many regimes, analytic or perturbative solutions are impossible to obtain in QCD, and we're limited to numerical simulation, that is lattice QCD. So in high energy physics, the theoretical physics and experimental physics kind of play complementary roles and inform each other. So on the theoretical side, we use these big machines like Perlmutter, and you running, these lattice QCD simulations to tell us what the standard model says about how these particles will interact with each other. On the experimental side, they also use even larger machines where they colliders, for example, where they smash particles together and see what the resulting shower of particles is. And then we compare these theory, prediction, and experimental results. If they agree, great, it means the standard model is working. If they don't agree, even more exciting, it means there's something to be learned. So an example of this is the muon G-2 experiment, which was in the news this past year. So back in '97, Brookhaven National Lab started running this experiment. So maybe I should introduce the muon first. So the muon is a fundamental particle in the standard model. It's electrically charged. It's basically the heavy brother of the electron. G-2 is a physical quantity associated with the muon that tells us how this particle behaves in a magnetic field. So Brookhaven was running a long experiment to calculate this quantity. And so this ran for some years, and then they computed they came up with the theory prediction. And there was a 2 to 3 sigma discrepancy between theory and experiment. And this excited the field quite a bit. If theory and experiment are disagreeing, one of them must be wrong or something. So the theory calculation at this point was based on some combination of perturbation theory, Monte Carlo simulation, and some data-driven inputs from experiment. Lattice QCD didn't really play a role at that stage. The theoretical underpinnings were there, but the computational resources were not at that time. So jump forward to 2017, the experiment was restarted at Fermilab, so they were going to rerun this experiment at Fermilab, taking a lot more data to higher precision. And this result ended up confirming the Brookhaven results. So there was apparently nothing wrong on the experimental side. And in this intervening period, these 10, 15 years, lattice QCD really came of age, and it entered the precision era. And a lot of this is due to the advent of GPU-based supercomputers, which gave us a lot more power to compute these things. So the first real lattice QCD calculation of this G-2 quantity came out in 2021 by the BMW collaboration, and their result kind of agreed with experiment now, disagreeing with the previous data-driven theory results. And so over the next couple of years, a lot of lattice QCD collaborations really concentrated on computing this quantity, really put in a lot of work. And in 2025, roughly the same time that Fermilab posted their final result, the G-2 theory initiative, now basing their calculation largely on lattice QCD inputs, came out with their result, and they agreed. So theory and experiment now agreed, and apparently there was something wrong with the earlier data-driven approach to calculating this quantity. So who are the lattice QCD people? So in the US QCD is kind of the overarching collaboration of Lattice researchers. There's over 200 of researchers spread out around 60 institutions or so. Within US QCD, there are multiple collaborations. Fermilab Milk is the one I'm associated with. There are others like Hot QCD, NPL QCD, and RBC, and some others that I didn't have room on that line for. Okay, so what are we trying to do in Lattice QCD? So we're essentially calculating the quantum field theory of a tiny femtometer scale volume of space-time. And we do this by, we represent this volume on a 4-dimensional lattice. And on this lattice, we represent the quark fields as a field of 3 vectors that live on these lattice sites. And the gauge fields, the gluons, are represented by a field of complex 3x3 matrices that live on the links between the lattice sites. A typical calculation in Lattice QCD involves 2 steps. So the first is to generate an ensemble of lattice configurations. And this is typically done using some kind of Markov chain Monte Carlo method to give us a sample of equilibrium gauge configurations. Step 2 is measurement. That's where we measure our quantity of interest on each of these individual lattice configurations, and that gives us an average value for that observable. Now, both of these steps are large endeavors, usually multi-year endeavors, and of course involve a lot of sub-steps that I'm just kind of glossing over. But one nice thing is these 2 steps are separable in some sense. Once we have an ensemble of gauge configurations, we'll keep that for years, decades, and we can perform repeated measurements on these ensembles. So I have this interesting plot from my advisor, Stephen Gottlieb, that kind of illustrates the multi-year effort that went into generating this one particular ensemble of gauge configurations. So the vertical axis shows the Monte Carlo time units that were generated, and the horizontal axis shows day of the year, and the different curves then show different years. So you'll see that we started generating this ensemble in 2014, and we got up to around 1,000 time units or so. What's really interesting is to see how much the slope changed in 2021 when we were running on Perlmutter early science time. So in that time, we were able to almost double the size of our ensemble. And hopefully we can do something like that again with early science time at Dowden. So like I noted, a typical calculation, whether it's ensemble generation or measurement, requires, is a multi-year effort, takes thousands of runs. A typical run may require hundreds of nodes using terabytes of memory and disk space. And when I was preparing this presentation, I was curious, what fraction of US supercomputer time is used by Lattice QCD? I wasn't able to find a public listing of AirCap awards, so I looked at the latest ALCC awards instead. And this showed that around 20% of the time of the ALCC time was awarded for Lattice projects, and about 5% of the total time was awarded to the Fermilab Milk collaboration projects. So given how much compute time we use, we as Lattice QCD researchers, it behooves us to make sure that our codes are running efficiently and we're using good algorithms so that we're using this time wisely. The code base that we're using is already highly optimized. We profile it every so often and try to squeeze everything out we can. But it's already quite optimized, so large speedups will likely come from trying new algorithms. And these speedups will translate directly to more science per awarded node hour. All right, so let's jump to our computational challenge. So in both ensemble generation and measurement, the main computational bottleneck that we run into is the need to repeatedly invert these large sparse Dirac matrices. And these matrices are quite large on they're typically, billion by billion matrices. So we want to compute something like, this X equals A inverse times B, where A is that Dirac matrix. And we'll do this by solving a linear system using a Krylov method like conjugate gradient. So the conjugate gradient algorithm, it's an iterative algorithm where each iteration will choose a new direction based on the residual at that step. So we know the convergence rate as it relates to the iterations. It's given by this expression, which there's no need to memorize. What's important is that the number of iterations that we need in order to reach the solution is given by the square root of the condition number of the system. And the condition number is the largest eigenvalue divided by the smallest eigenvalue. So in a sense, it's the range of the eigenvalue spectrum of the system. So that leads us to our problem. So in this plot on the left, I have a plot of the number of CG iterations needed to reach solution. And this is plotted as a function of our quark mass. So you'll see that the vertical axis is logarithmic. So it really blows up as we decrease the quark mass towards the physically interesting part, which is towards zero quark mass. And since the condition number depends on the eigenvalue and the eigenvalue depends on the quark mass, as we decrease that quark mass, we get this, the smallest eigenvalue gets very small, and so we get this explosion in the condition number of the system. So our goal is to take this curve and flatten it. And there are two possibilities that we're considering. The first is eigenvector deflation. That's where we explicitly remove these low eigenvalues. We solve them exactly, and then that leaves a better conditioned system for the CG to work on. The other approach that I'll look at is multigrid, which solves the low eigenvalue modes on coarser grids where they're effectively no longer as small. All right, so with eigenvector deflation, so we have some set of the low eigenmodes, meaning the eigenvectors associated with the smallest eigenvalues. And we use these we construct this projector, we apply it to the right-hand side of our system in order to project those low modes out of the vector. And then we pass this resulting vector into our CG as our initial guess. And now CG only has to deal with the easy parts. So effectively, what we accomplish this way is we remove the critical slowing down from the conjugate gradient part of our workflow and shift it to the eigensolver part. This is fine if we have a workflow where we're doing a lot of solves per Dirac matrix. Nevertheless, eigenvector deflation will probably not be the long-term solution because as the volume increases, it becomes more and more costly. So we experimented with deflation on a Frontier and most known Perlmutter really. And some notable results that I'd like to point out is that we found that if we periodically restart the CG, we can actually use sloppier eigenvectors. using single precision eigenvectors instead of double precision. This reduces our memory footprint by a factor of 2 and means we can run on half as many nodes. We also got the block eigensolver working, which improves our eigensolve by a factor of 2. But in the end, the big number is, the main number is that we were able to get a 10x solve time speed up using eigenvector deflation. And so this is just an illustration of that. So same kind of plot as before, but instead of CG iterations, I now show solve time. Orange curve shows the CG solve time. Blue curve shows the eigenvector deflation solve time. And if you take the ratio at the light quark mass of the two solve times, you get that 10x improvement. And you'll see that the eigenvector deflation, the curve is essentially flat, meaning critical slowing down has been eliminated there. But I also want to point out the solve times we're looking at here are a couple of seconds for deflation or maybe 50 seconds for CG. Compare that to the setup time needed to generate the eigenvectors, which was 3 hours. So this approach will only be useful if we're doing hundreds or thousands of solves per set of eigenvectors. So in terms of pros, we get a 10x solve time speed up. Drawbacks are we need thousands of eigenvectors, which means we have memory usage of tens of terabytes, and we have a large setup time that takes hours. So it's useful for if we're doing hundreds or thousands of solves for each unique Dirac matrix, and that ends up meaning it's useful for certain types of measurements for us, but it's not useful for ensemble generation. So what about multigrid? So just a very brief technical aside, in Lattice QCD, there are different ways that we can discretize the fermions, different ways of representing fermions on the lattice. There's Wilson fermions, staggered fermions, domain wall fermions. I won't go into the details, but to say that in Fermilab MILT, we usually concentrate on staggered fermions. So we're interested in a solver, in a multigrid solver for staggered fermions. And this proved to be a lot more challenging than for some other fermion types. But the key turned out to be a particular spectral transformation that took our eigenvalue spectrum, deformed it in a way that was a lot more amenable to multigrid. And the details of all that, if you're interested, is given in these papers below. And along with that, there's a lot of ensemble specific tuning that is required in order to get multigrid to work. So in terms of how multigrid works or how we use it, so we use a 4-level multigrid preconditioner for an outer Krylov solver, the outer solver GCR. And so during the setup phase for our multigrid, we need to compute these near null vectors for each of these levels. We need to construct these coarse operators, and we need at the coarse level, we do deflation, so we need eigenvectors for that. So that comprises kind of the setup phase. Then in the solve phase, when we're running the actual solver, it'll jump up and down between the different levels using those coarse operators that we constructed. So we used the CUDA software library this is CUDA with a Q, to compare multigrid with conjugate gradient on MILT's ensembles. And the results are averaged over 3 gauge configurations, three different lattice configurations. So same kind of plot as before on the left. The green curve gives the solve time for conjugate gradient, and the orange curve at the bottom gives solve time for multigrid. This is with CG and multigrid running on identical resources. And if we take the ratio at the light quark mass of the CG versus the multigrid, we now get a 17x speed up. The curve at the top, I show now the setup time for multigrid. And the setup time is highest at the light quark mass. And here we see a setup time of around 1,000 seconds, so about half an hour. But compare that with the 3-hour setup time coming from eigenvector deflation. So on the right, the same data is presented in a slightly different way, where now the intersection of a curve of a solid curve and a dashed curve shows the break-even point for a specific quark mass. So the dashed curve gives the CG runtime. It starts at 0 since there's no setup time. And the multigrid is given by the solid line, which has a much flatter slope due to being a faster solve time, but it's also shifted vertically because of the setup time. So the intersection point shows that we need maybe something like 15 to 18 solves to break even with CG, compared to, say, hundreds or thousands of solves needed to break even if we're using eigenvector deflation. So if we compare multigrid versus deflated CG, we found that multigrid has almost a 2x faster solve time. It also runs on fewer nodes, has faster setup time, and the setup vectors take up less disk space. But the drawbacks are that multigrid requires a lot of parameter tuning. There's lots of knobs to tune, you know, how many setup vectors to use for each level, what tolerances to use in the solver and all that. These things need to be tuned in order to get the good behavior out of the multigrid. Some more technical drawbacks with multigrid are, for example, that the setup vectors are quark mass dependent, which means if our workflow wants us to compute, if our workflow wants us to do solves at many different quark masses, then multigrid will require us to repeat the solves at each quark mass. So in summary, in Lattice QCD, the Dirac inversions are these large sparse matrix inversions are a computational bottleneck. And this is because conventional conjugate gradient suffers from this critical slowing down problem as we approach the physical point with the condition number blowing up there. So we end up needing new approaches. And in our recent testing, we looked at 2 different approaches on Perlmutter. And with eigenvector deflation, we found a 10x solve time speedup. With multigrid, we found a 17x solve time speedup. And these speedups should translate directly to more science per node hour, which is what we're really after. So thank you for your attention. Questions?
Thanks a lot for that talk. Can you tell me roughly how much you use in a year? How many node hours for the your group? I'm a new user, so I'm just trying to understand what's possible.
Million or so. I'm just going off of memory here. I don't know what our ERCAP allocations are, but I think our ALCC was on the order of 1 million. I think it was 2 million, but it's split between different groups.
This is under high energy physics.
Yes.
One more question.
You considered also direct solvers instead of iterative solvers. For example, I know like the DSS library, NVIDIA supposedly scales out to full systems, does sparse direct solves on GPUs.
These are systems of size like billion by billion complex. are there direct solvers that work on large systems like that?
So I mean, I think this cuDSS library, I'm not that familiar with it, but I think that is the target, is to do like these very, very large sparse direct solves using both CPU and GPU. And I mean, it's a very recently released library, but we've used it at least, we haven't gone to billion, but we've used it and had some success.
We have not looked into that, to my knowledge. Could you say the name of the library again?
cuDSS.
CUDSS. Thank you.
Thanks so much. Yeah. Okay, so we have a few more talks coming up now. Igor, you can come on up here if you want. I do want to mention that there are already, I think there's a fresh batch of coffee and a few cookies. So if you need a little sugar or, you know, so a little pick me up. I know waiting till 3 might be too hard because everybody likes cookies. So you feel free to go grab something and come back in. Okay, so let me.
Microscopy. I do computational imaging, so I
Oh,
really,
cool.
I really like it.
Microscopy.
I'd like diffuser optics.
Oh, cool.
I do some, I'm actually, maybe I can email you because I had some questions.
Sure,
Like,
yeah.
actually, questions about what I'm doing that I think your perspective actually be helpful.
Sure, I'd be happy. You want to wait just a minute? just
Yeah,
so
wait.
people-
Yeah.
Yeah, we're not in a huge rush because actually one of the talks canceled, so we can actually take our time a little bit. Everybody stretch, everybody. This is actually the UC session apparently because it's UC San Diego or UC San Diego. And then, well, the next talk is the lab, but UC Berkeley. And then the last one is UCLA.
Perfect.
So this is the UC session coming up.
Yeah, I'll wait. Just let me know when it's done.
Yeah, sure. Maybe once people kind of come back in, whenever you're ready. Feel free.
Thank you.
The number, you know. Those very good.
Yeah. Well,
Are there other labs people that have?
the number I gave, that was for just. That wasn't a full number. So.
Not dedicated.
A frontier and yeah, so frontiers is like over, you know, and this is a new system. So, Steve, my advisor, posted the bomb one baseball television was 435,000 GPU dollars. So that's across two different. Or, yeah.
He's on one so kind of. Trying to understand what's possible.
Yeah, it's hard to know because like, I don't think they're probably isn't. No, because I wasn't able to find them. I'm like, it would be nice if they would.
I think that one's for figures.
Maybe it was not in my interest. So they want to be.
Yeah, so,
That's 25 billion
signups here
years.
for the course, so ask Celeste, she's ready.
All the other people.
She'll be back in a second, she's the one here, she has this tour sign up, so there's one today at 3 and one tomorrow at noon.
Okay.
Well, we're.
Okay, why don't you go ahead and start, people will hopefully,
Yeah.
Yeah.
20 to 30 of us. So, I mean, it's right now, we're different. Yeah, it's not like one person is using all of this time.
Yeah.
It's,
Okay, I guess we can start.
Yeah.
So, hi, my name is Igor Sfiligoi. I come from UC San Diego. We are the Supercomputing Center. That's very relevant. I have been working on CGYRO related stuff for a while with the main authors, with Jeff Candy and Emily Belay. And I'll go all over how we went from having a bunch of independent CGYRO simulations and figured out that if we run them instead of ensembles, we actually get some decent performance improvements. So that's what the talk is all about. So we had to talk about magnetic fusion before during the remote presentation. So it's a little bit on the same theme. Magnetic fusion has the promise of creating large amounts of clean energy, so it's very promising. We are getting close to practical applications, but we are not there yet. And similar to the QCT talk, we have experiments, but we also have theory. And the reason is, yes, you have to try stuff out to see how they work, but you need the feedback from the theory to actually understand what is actually going on in the detector and to plan on what to do next after you see what you got from the detector. And of course, whenever you see something, you see a measurement, but why it happened, that's where the theory comes in. And a lot of that is driven by simulations. So here we are mostly interested in the tokamak-based fusion. There are other fusion approaches, but CGYRO has been developed to simulate tokamak fusion processes. The important thing in a fusion reactor, like it was mentioned before, it's having good confinement. So the plasma stays where it wants to be and doesn't hit the walls, make damage and stuff like that. And the confinement in the end is really driven by the turbulence inside the plasma. And this is because of unstable plasma waves. So we really need good simulation, first principle simulation tools to understand what's going on inside the plasma in order to get us where we need to be. Fortunately, really good predictions come with a really high computational cost. In fusion plasma, for the longest time, we needed HPC. You don't know if you know it, but the first HPC system in the US was created to support fusion plasma simulation. It happened to be at UCSD. So SDSC actually happened to host the supercomputer to do fusion plasma simulations. Now, computer has scaled a lot, way more than what fusion plasma needs. So we don't need whole system simulations anymore, that's my knowledge. We still do large runs that take a large fraction of system from time to time, but we are not the biggest user anymore. We used to be. NERSC is one of the systems that we use. Which brings us to CGYRO, not by far the only fusion simulation tool around, but it is a very popular one, and it's very good at predicting what happens. We believe it's the best. I guess I know others have other opinions, but I do believe it's the best fusion simulation tool around. It's a new Lyran gyrokinetic solver. It has been developed and optimized for collisional, magnetic, and multi-scale simulation, so it can really span the whole spectrum on anything you want to simulate inside fusion plasma tokamak setup. And it was initially on CPUs. We have been using it in Cori, for example, here at NERSC. We have ported it to GPU from the times of of Titan, so we have been running on GPUs since forever. And we're running per matter now on the GPU partition. We can run on the CPU partition, but it's too slow. Some small simulation run there because it's easier to get allocations sometimes there, but we really prefer to run on GPUs. The part that is really important for this talk, it's the fact that to get high fidelity, CGYRO implements the complete Sugama electromagnetic gyrokinetic theory, which has a collision operator in 2D diffusion in velocity space and is implemented using the implicit time advance, which results in a very large constant tensor structure, which we will call CMAT from now on. You'll see CMAT referred a lot of time, which is computed once per simulation and then used repeatedly during the simulation as you progress through the time steps. And we do this because it really speeds up the simulation, but it is big. Turns out this single tensor structure, it's what dominates the memory need of CGYRO. This structure by itself, it's order of magnitude bigger than anything else memory-wise inside CGYRO. Fortunately, it's not optional. Similar to what we saw in the previous talk, we do this for a reason. Yes, there is some penalty to pay, in this case, memory, big memory use. But if we didn't use it and try to do on-the-fly compute of what we do right now at once, everything will be orders of magnitude slower. So we take the penalty byte. We require a lot more memory, which means we have to spread across more nodes, which means more communication, because of course you need to synchronize different parts of your simulation. But even with the communication overhead, it's still a big win. So we want to go this path. We don't think there is an alternative, but there is a penalty to pay to doing this. Now, I said that this is the biggest memory use. Can we do something about it? So the first thing to notice is I said it's a constant structure, which means it doesn't change during the simulation. But is it really unique between each and every simulation that users are going to run? And the good news is actually it's not. While this constant structure is computed for each simulation independently, it doesn't depend on every single parameter that is used for the simulation. Only a subset of parameters is used for to create this constant structure. So indeed, there are many studies that run variations of the simulation where this constant structure actually stays constant across each and every simulation. So this is good. So we don't need really to recreate it every single time. Fortunately, this doesn't help us if we run simulations independently. We still need all the memory for the simulation to keep it in memory, because reading it from this would be absolutely too slow. We can't even keep it in the CPU attached memory, move it between CPU and GPU. That's already too slow. So it has to be in GPU memory, for example, on GPUs. So after that really sank in, and we didn't really realize this until like a year ago, we said, okay, so we have a bunch of simulations that all share the same CMAT. How can we make good use of it? And we said, well, what if instead of running each simulation independently, we ran it as an ensemble, right? So can we do this? Yes, we potentially can, but this also means the whole ensemble has to run as a single MPI job because they have to share something between all of them, which was not something that we could do previously with CGYRO. So we developed a new tool that is we call XGYRO, multiple times CGYRO, that will aggregate a bunch of simulations. And ideally, we want that CMAT to be shared across of them. So that's what XGYRO is. And I'll go a little bit more in details how we did it. But just to the first approximation, we keep most of the CGYRO code, add a little bit of glue, change a little bit how the problem splitting is done so that we can actually share CMAT across all of the simulations. That's about it. So the code changes were really minimal. I'll not show the code changes, but trust me, it's like 1% of the total code base or less. So it's not a big change, but it gives us a decent speed up. So here is, before I go into details, I just want to show that it actually works performance-wise. So if you look at how we have remote presentation, remote people. So if you look what you have, let's move to this. How much time is spent in CGYRO doing compute and how much it goes into communication. Yeah, we spend almost half of the time doing memory movement between nodes, and this it will be clear a little bit later why that is. There is a lot of essentially transforms. We do a lot of odd walls that expensive, and also a lot of all reduces. It's basically we need to move a lot of data around. So the fact that we have spread across multiple nodes, we do pay cost. But when we change that and run it as an ensemble and where we share CGYRO, CMAT with XGYRO, you see the amount of communication overhead gets drastically reduced. So we get about 1.5x speed up in this example. And I wouldn't say that is completely typical, but for a large fraction of our simulations, it's in that ballpark. And that's because we reduce the communication over costs by like, I know, it's like a factor 5, which then overall is a little less. This also will give me a little more incentive in trying to speed up the compute part, because in the past, when you have so much of communication cost, speeding up the compute doesn't really make a lot of sense if you cannot address the other one. Since we can now address the other one, it puts more priority on actually shrinking the compute time, because it actually makes a big difference in the total runtime. While before, I speed it by a factor of 2. Yes, I got a 30% speed up. I'm not saying I wouldn't want to do it, but it's less of an incentive. So hopefully I motivated you that it's what we did makes sense, at least performance-wise. So how did we get there? So let's start in how actually CGYRO works. I'll not go into the physics of what's going on. Full disclosure, I'm not a physicist. I hardly understand what we are calculating here. I'm a computer scientist. So I'll focus on what I understand, which is how compute works. And how compute works in CGYRO is that we have most of the structures are essentially big 3D tensors, with the 3 dimensions being the configuration, the velocity, and the toroidal dimension that will, and I'll use NC, NV, and NT all over the place from now on. The only exception is CMAT, which is a 4D, and it's essentially quadratical in the velocity dimension, and then you have the other two. So that explains why it's so much bigger than anything else, because NV it's usually something like 1,000. So obviously, if this is 1,000, this one is 1,000 times bigger than everything else. Even if you have tens of the others, they are still an order of magnitude together, an order of magnitude smaller than this single big one. The way we scale some across multiple nodes, because obviously when you have a big memory problem, you cannot fit in a single node, not just compute, it's really you cannot fit in the memory that you have available, you have to spread it. And CGYRO has 3 phases, and each phase needs one whole dimension. The way the problem works, you always need one full dimension in order to compute. So this is not a classic stencil one. We actually need the whole dimension for various reasons. So we essentially move between 3 different phases where we keep one dimension complete and the other one can be distributed. And here you have an example, but yes, those are the 3. So the streaming phase, which is where CGYRO starts, needs a complete NC. The nonlinear one needs the complete NT, and the collisional ones needs a complete NB. Now, when we try to run an ensemble, if we have want to have any hope to share CMAT, all dimensions might be the same, right? Because in order for all the values of the CMAT to be the same, at least the dimensions must be the same. So conceptually, what we get is repetition of a lot of these simulations plus something that connects them all, because we need a way to share, so we need to have a common MPI communicator in order to share that information. So that's how we start before trying to do anything. Just get a bunch of CGYROs, get a common communicator, and you start there. Now, I will ignore the toroidal communicator, the one on NT, simply because there is never a transition between, there is never a reason why you would need CMAT for that. And it comes down to how the various transitions between different phases are. So we have a transition between the streaming phase to the nonlinear phase and back, and the streaming phase goes into the collisional phase and back, but there is never a transition from the collisional to the NT phase. So since the collisional phase is the only one that needs CMAT, and we have never a direct transition between the two, I don't have to worry about it. So for the purpose of this work and inside XGYRO, we completely ignore that part. All the code that has to deal with the nonlinear phase remains completely identical, because there is I don't have to worry about it. Now, the part that I do want to worry about is this transition, right? Going from the streaming phase, which has the whole NC, into the collisional phase that needs the whole NV. This is essentially an all-to-all, back and forth, and different codes run in the two, but essentially the important part is how the memory is being essentially transposed from one representation to the other. There is an additional thing that makes this a little, a little non-trivial, is the streaming phase also has a bunch of steps where it needs to do or reduce of some of the values, and that goes against all the processes. And since the processes involved here and here are exactly the same, we were using the same communicator. There was no reason not to do that. However, the moment we want to share CMAT across all of the processes, that's not true anymore. Because the all-to-all now takes transpose now gets the data structures of many independent simulations, translates them into transposes them across all the processes, because now CMAT is distributed across all the processes. So I must aggregate the data of all the simulations into all the processes because it's the only way for each byte to actually has access to CMAT that they need and back. And that is very different than the all reduces, which only talk to the processes that are specific to that simulation. So I have to split, essentially add a different communicator for all reduce versus all to all, which conceptually should have always been the case. We were just trying to be cheap and reuse something, but conceptually, it was like that from day one. And that's really the only thing that needed to be done. So once you do the transpose from all simulations at the same time into the collisional phase, at that point you have CMAT that is shared across all of them. So the collisional phase essentially computes, uses CMAT to do the collisional step for all the simulations at the same time, and then you redistribute them back to their independent things, and they go independently again. So you have this synchronization point where you merge them together, and then they go separately. And everything apart from this part only operates on their own nodes for the simulation, which is a small subset of the whole thing. And the only time you actually need to worry about going across all the nodes, it's in the collisional state.
You have like 30 seconds.
Oh, 30 seconds. Okay. So just to say here, it's not only when you have few nodes, it also helps scaling to more nodes. And I just wanted to show this slide where I emphasize the collisional state is the only time you need to go across all nodes. All the other steps really are in within the small steps. And if you look here, the collisional part, it's really cheap. It's everything else that was expensive. And by keeping it localized to fewer nodes, we pay a lot less penalty there. And just the summary, and I don't need to read it. So.
Okay, thanks. Any quick questions for Igor? You're gonna be here both days, right?
Yeah.
Tomorrow? Okay, good. All right, well, ask your questions at the coffee break. Thank you so much, Igor. Okay, so we have you. Sorry. Well, LBL, but we'll say UC Berkeley, right? Okay, so you are, did you join us?
Yeah, I joined.
Okay, good. So you should share. Yeah. All right, sounds good. I'll try to give you like a 1 minute warning.
Okay.
Okay, sounds good. Thank you.
Yeah. I graduated from UC Merced, so you know.
There we go.
Anyway, okay. So some easy stuff, it's not about biology, which there are not a lot of maths involved in, and then maybe wake people up a bit. Okay, so today I'm going to talk about AlphaSAXS model that we developed reconstructing protein structures with physiological relevant conformations from skull angle X-ray scattering data. It's pretty long, but I will later explain each part of this in my slides. So the protein I'm going to describe a little bit different than what people usually see in an AlphaFold, which I think a lot of people here are familiar with. So many proteins actually contain intrinsic disorder protein regions, which lack of a fixed native structure instead of exhibiting a constant changing conformational ensemble. Later, I will show a video. But here, if you look at this protein, I think it's easy to guess that the center part is with structure and all the red part are without structure. Usually people will think, those proteins without structure, maybe just AlphaFold make a wrong guess. Actually, not exactly, because those proteins actually should look like this. Sorry. Something like this. It's highly dynamic and keep changing. So basically, you don't have a native conformation. If you think it as a data, then you'll think it's an NA in panda data frame, right? It's just like not exist. Whatever prediction AlphaFold will make, it will not be accurate. how important are those regions, right? Because people keep claiming like, the DeepMind and all those kind of companies keep posting news about, okay, protein structure solved problem. White House thinks so. China thinks so as well. And all people who are not familiar with protein structure think so. Yeah, but actually there are widely exist proteins with IDR. So if we search all the proteome across different species, over 40% of human proteome have at least IDR regions, right? Some of them have extremely long IDR regions that looks like spaghetti. So that means for this basic structural prediction task, AlphaFold didn't do well in half of those proteins, but we just pretend we don't know since that's all we can do. More in detail is that AlphaFold have low accuracy in predicting this spaghetti structures and usually a label like red color. So if you see red color in AlphaFold, it's that highly likely it's a disorder protein. They did a good job on that part. They will tell you what they did wrong. More importantly is that we evaluate all other methods that developed recently in Cas16, which is last year. That how good are they generating those ensembles of flexible regions? Some of them using diffusion, some of them using MSA subsampling, some of them using flow match, or all those kind of new technique. None of them do a good job. If you look at the bottom corner, it's ideal case, and all those predictions are far from ideal case, which that means it's not accurate. It's not accurate, it widely exists. Is that important? This is a slide I just added this morning because I want to show that how important it is. Think I joined this lab 2 years ago, and at that moment AI for drug discovery is pretty popular, and I believe AlphaFold is discovered 4 years ago. Like in silico, those companies established 4 years ago. So they're trying to use AI to accelerate drug discovery. Their typical claim is that usually drug discovery takes 10 years. Now they can accelerate it, can make it fast. Now 4 years passed, what happened? So I asked ChatGPT, I don't want to search all those papers. I asked ChatGPT, it solved for 2 minutes and 36 seconds. And give me a short answer that 0 of those AI discovery companies produce any medicine to the market, and only 1 passed phase 2. The phase 2 is the phase that showed your drug actually works in human, but there's a phase 3 that you need to widely test a lot of population. So, AI discoveries accelerate the drug discovery and accelerated from maybe spend 10 years to 9 years. So pretty good. And why this is happening? One of the most important things is that the model right now, AI model right now is not good enough. And we are trying to ignore that. So the consequence is that after 4 years, we still won't be able to find drugs. That's a problem, and we need to solve the problem, right? How should we solve them? Basically, I'm working in SAXS beamline. It's in bioscience division, but actually located at ALS. So it's how our work is like a user facility. We take care of user business across the entire world. Now more in United States, so we will have less collaborations. What people did is just they have a protein that they're interested in with flexible regions, we change conformation in solution, all those kind of things. They just express protein, extract the sequence, send a sample to our beamline, and we will get the data and do the analysis. What data we will get? We just shine X-ray on the sample in the solution. We'll get intensity from sensor with some profile with a lot of noise. Then I need to do another analysis to generate a model and validation, all those kind of things. So this beamline has been exist for, I believe it's 20 years, and they have high throughput experimental techniques that works pretty well. The only concern we have is that it takes too much manpower for data analysis. Why? Because what we should do is that we need to generate possible structures. We may use different kind of MD simulation, our in-house buildable MD tools, so all those kind of things, convert to SAXS curve and fit into experimental data. Even though we only have 3 steps, but it takes a lot of effort, and it's not good for high throughput experiments. The SAXS itself is really important for those flexible protein regions that I showed before that AlphaFold cannot solve. So I'm thinking about, can we combine the SAXS and AlphaFold so that we can make the data analysis high throughput, will solve the problem AlphaFold cannot solve? So that's what we're gonna do, right? We directly get protein ensemble by just integrating this SAXS input, this kind of experimental data to the AlphaFold to generate possible structures. So in this case, we combine two methods to generate a quicker method that's maybe better. If we do that, we have two representations to change. There's two encoded internal representation of AlphaFold. One's called MSA. It's a genetic database. Basically, it's the main job of JGI. And the other one is distance matrix, which is a structural based data search. It's more like, ALS and the structural beamlines. Those internal representations are crucial for AlphaFold. Because AlphaFold is written in JAX, it's not in PyTorch, so we didn't actually change the AlphaFold itself. We changed OpenFold, which is written in PyTorch and easier. And this is our primary architecture that after the embedder, we introduce two cross-citation of SAXS, P of R curve, and then we retrain it with PDB dataset, with recycling, and with hyperparameter training, with OpenFold and PyTorch. We specifically change training structure to represent as possible movement in protein. For example, one statistical structures will be fixed loops, will be input into program to generate a more dynamic ensemble. You can see that there are all potential movement to simulate how it exists in a true environment. And we also pick the NMR data, which inherently has those dynamic structure. So that means all the input training data set in our new model is considered to be flexible and dynamic rather than a single structure. And then we also compared it, try to test it on protein that has at least two conformations, right? We have 91 pairs of protein that have same sequence, but two conformations, 1 and 2 AlphaFold usually cannot get any of them. And then we'll select protein pairs that AlphaFold did a terrible job, used as a test data set. We also remove all related MSA structure from our training data set to prevent data leakage, which AlphaFold didn't do. But I just in case, we really want to remove that to get a real performance test. So here is just one quick example of how it performs compared to the AlphaFold. If you look at the gray area, that's our target ground truth. And left side is AlphaFold. This domain, the angle are completely wrong, and all those kind of orientational are wrong, right? In the NMR and NMA test data set, we see a closer match. The structure, which RMSD 1 is equal to 2.1, 1 is RMSD equal to 1.73, it's improvement like 30 or 40%. On the right side is the SAXS curve that we get, that we will see in the experimental data. Sorry, we compare the AlphaFold target and our two trained structure. We'll see that our trained structure minimizes the difference between the structure, between the PLFR curve of SAXS and the ground truth. So that means our structure can understand the SAXS data and try to minimize that. This is just one example. And then another important feature of our model that I can show another example is that for a protein with exactly same sequence, but two very different structures. The first column, first row and second row are one protein with the same sequence, but very different structures. Then we can see AlphaFold didn't do a good job, but our NMR can try to generate two diverse conformation match the SAXS. And they also apply to the entire test data set. But there's one key problem that we will solve it later, and I will show a later slide, is that despite the shape of targets looks a little bit similar, basically the electron density overall looks similar, the structure actually not look that good. So we'll fix it later. But anyway, it got a good SAXS curve, so that means it tried to minimize SAXS loss and match experimental data, but somehow we push it too much, change it too much to make the protein structure a little bit distorted. So overall, if we look at the machine learning criteria, this is older data. We run a new version, we have a further improvement, but this is our average performance on RMSD to show our improvement. And this is why we are being accepted by an ICL workshop, and then we're going to submit it to Nature Communication in November 9th, the special collection. Anyway, that show the overall performance improvements of our machine learning model. However, we are not satisfied with it because first, even though we can generate distinguished structures with some dynamic of the protein, it doesn't look that good. And then the accuracy improvement is not that well. More importantly is that I promised in the first slide that I will generate some movie that show that dynamic of the protein. However, all the structure I showed before is like single structure or something like that, right? This doesn't match our scope. So what do we did? So what we did is that we add another inference time optimization layer in one of the single representation, internal representation of our AlphaSAXS model. This approach has been proven effective in many papers. And what it does is trying to generate multiple structures and optimize some single layer and some layer added here to reduce the SAXS loss. Our purpose is that to introduce minimum change to those flexible regions to let them reasonable, improve RMSD and SAXS curve fitness, but do not disturb the protein structure too much like what we've seen before. What it generates is something like this. It's just not a movie here. I overlay all the structures, that all the flexible regions generated by the structure. The purple one is the original one, the single state we generated with AlphaSAXS, and all the blue region is the ensemble we generate. So basically, we can generate a dynamic ensemble of the protein that we can consider as moving or the possible movement of the protein. And especially if you look a little bit closer to the structure, we can see all the change are in those intrinsic disorder region or flexible regions that I mentioned before. The change a little bit here is a little bit more, here is a little bit less. The RMSD accuracy compared to ground truths, some of them improve a bit, some of them decrease a bit. That doesn't mean the accuracy change a lot. It just means that we show more diversity in the intrinsic disorder region because, as I mentioned before, those regions do not have a single structure, so they actually don't have ground truths. On average, this technique has a good performance. This is the baseline of our single structure performance. The average performance of our model is about the same, but the best performance of our model have about 0.4 improved RMSD with a high conformational diversity. That means how dynamic the protein we generate are. And here on the x-axis is ensemble best at RMSD. So that means in this case, we generate a protein structure that are accurate and are dynamic. However, it's still not like reach a really high accuracy. If we can generate every protein at RMSD equals to 1 or 2, that's really accuracy. But now, according to our training and our strategy, we will only be able to improve it to like about 4 angstrom RMSD. So that's basically is our method. That what we do is that we combine the SAXS and AlphaFold, trying to let AlphaFold generate more structure fit into the experimental data. And we also produce an ensemble method that can generate protein dynamic, which are 2 core capacity that drug discovery company wants. And that's what's the next step direction we want to work toward as well. But there's something I want to discuss a little bit more about, I think I showed this in the Montreal Data Conference before, but I want to also show it to this audience as well. It's like, I want to emphasize the reasons for success of AlphaFold from a biophysicist perspective, to point a little bit more about how we think AI should proceed. Because all the AI for science concepts, there's only one example to support that is the AlphaFold. And, I want to dig a little bit more into it so that people understand a little bit more about how we think about it. So the success of AlphaFold is not an easy task. It's not a common thing in the scientific world because we need 4 factors to make it successful. First, we need tasks are clear defined with a mathematical interpretation, which is structural biology, and has been developed for 50 years. So we can know that how to quantify the structure and how we see this is an accurate structure or wrong, how do we represent it? The second thing is that we need a gold standard data set that are available in a ready-to-go standardized format. That's a PDB database. There's a lot of effort involving the UCSD and the supercomputer center there, but also all across the entire world, including the Berkeley lab, right? We established the PDB database that's pretty standard and pretty easy to use, even though the latest format is not that easy to use. Pretty good compared to other format. The third thing, more importantly, is that we have one or more quantitative metrics that when people achieve that, we know they succeed. So that's why AlphaFold received our Nobel Prize so quick. That after they win the task, there's no doubt they solve the problem or the best model in the world. So that as long as you pass the test of CASP, you know you won, right? That's another important thing. And last part is that we need a state-of-the-art method that's ranked in an updated leaderboard. We cannot randomly publish paper everywhere and claim that we did a good job, but we don't have a leaderboard that's widely assessed by expertise. So all those four factors are important for AI for science and should be considered when we think about whether a problem is solvable by AI for science or not. And that's why I show it here, and I really emphasize to the audience so that people can understand a little bit more about how biophysicists think about AI for science concept, which is a little bit different compared to machine learning scientists. And I want to thank all the people working here, on this project. So Stefan Prince, which sit over there, is a part of the CBG, and also Oliver and Andrew Child as part of computational side of Berkeley Lab. And Kanapriya, Greg Hura, Susan Tsutakawa, and me are from bioscience, molecular biophysics and integrated bioimaging. So the collaboration between computer science division and bioscience division driven this project. But the most important thing I want to shout out is the NERSC Generative AI for Science project. They give me a huge allocation in 2024 that support me to finish this project. Otherwise, we won't be able to have enough GPU hour to finish all those things and submit it to the ICR workshop and NH communication. So I really enjoy this kind of special project setup that can let us unleash our full power in developing biology related AI models. So, and yeah, that's it for my talk. And if you have any questions, thank you.
We have a couple minutes if someone has, yeah.
Oh, go ahead.
So thank you for the very nice talk. I am wondering if there's any times when you have multiple candidate structures that all could present the same SAXS data, and you would have some like ranking of them instead of being able to solve just one structure. And then if this is the case ever, if you have these more robust computational problem pipelines, does this make the problem worse or better?
Okay, so yes, so technically speaking, since SAXS serves as one-dimensional data, we can push atoms so that there's an infinite number of structure can fit into SAXS. In our case, our approach is more like introduce variation to a ground state or a baseline state. So we have a ground state, and then we use loss function to push a little bit more to explore the neighbor space so that we can find several structures and fit into the SAXS. Well, also, because when they're training, we also use the AlphaFold loss function. So it fit both in the AlphaFold loss function and SAXS loss function. So that's the way we try to minimize the search space to avoid that problem. If I do some experiment, if I push it too hard, way too hard, to search a little bit more deep into the SAXS space, it will have a better fitting result into the SAXS, which is good for those proteins that change a lot of conformations. But what happens is that it may push part of protein a little bit more fragile. It's like the bound length may change a bit, all those kind of things. So that's a part of thing that I cannot fix. I use some PLDT mask, I use some relaxation, but it doesn't work that well. I think more realistically, we should combine not only SAXS, but with NMR or with Cloud EM. We should introduce more constraint. The more constraint we introduce, the more certain we know we are correct. Because and I think that's the approach to do that, rather than just rely on the AI model itself. So we need to introduce 2 or 3 types of experimental data, each of them give us some constraint.
Yeah, that makes sense. The correlative nature is very helpful. Cool, thank you.
I think I like the ending of your talk, your perspective on AI for science. I think one of the reasons why AlphaFold was such a big deal is because they actually put like a biology problem into machine learning parlance, right?
Yeah.
So it's like AlexNet and ImageNet, like all the things on your list, like most progress in machine learning kind of follows almost that same like list of ingredients.
Yeah.
And like I wanted to know like what you think about like where do you think like the community is failing and to like align to that sort of perspective?
So why there's a CASP with a 30 years? So there's the PDB, the CASP, and all those kind of community. When they're establishing, those biophysicists are really confident, even though at that moment computers are not that powerful. They believe that protein structure problem can be solved by proteins as long as we have enough data.
Right.
So they know it will be solved somehow, and then they try to build those milestones on it and try to make it a little bit robust and to help make it a little bit more helpful for people to develop it. For example, before AlphaFold, the David Baker, who also won Nobel Prize, you see in all this architecture to predict structure, they did not do good. They did a state-of-art job, which is terrible as well. But but people are just believing in the power of computation. They know it will be solved by computational work and it will be solved by AI. 30 or 50 years ago, it's just a matter of time. So people start to not think about, okay, how should we develop an architecture to solve the problem? We just more data, a robust leaderboard, and more people get involved into this activity, it will be solved eventually. We don't need to worry about when and how it will be solved. It will be solved. People are confident about it. I think that's a big difference in the protein science community is that nobody worry about, okay, can I publish conference paper, right? There's 10,000, 20,000 submission there. Can I win the prize and get a professor job, for example, as me as a postdoc, right? They are so chill that they don't worry about, okay, whatever, who solved the problem is all right, in 30 or 50 years, the problem will be solved. So I think that's a good attitude, but I don't think I'm not that chill, but no.
Okay,
Yeah.
thank you, Feng.
Yeah,
Thank you
thank
so
you.
much. Okay, so we're just, we're a little bit behind, but we can just shift things a little bit.
Here we go.
Okay, and just one more thing I want to mention, there is going to be a tour after Zvi's talk. If you want to go on the tour and you didn't sign up, I think that's okay. We have plenty of spots. So Helen will take you all down to the data center. I think if you've been down there before, you may want to go again, because I think things have changed, right? I think things are different now. So yeah, Nick is saying it's cool. So even if you've been, just go. Okay, thanks, Zvi. Take it away.
Well, thanks a lot. It's a real pleasure to be here. So my group, we're new users. We got our first time back in July. That was at the end, it amounted to 30,000 hours, which we just used up. I'm really happy to be here to meet the people who make this thing work. So I've used other supercomputers, and so far this has been by far the best one. I love those messages that I ask a question, I get immediately, in 4 hours, I'll get the answer. It's always been true so far. Okay, so I'm going to talk about using supercomputers for kind of an unusual problem. It's high precision calculations and gravitational waves using collider physics methods. So I'm a particle theorist. You could say the first thing that you may be wondering about is how can elementary particle theorists help with the problem of gravitational waves? It looks completely different. So in collider physics, you know pretty well. Is there a pointer? Maybe I'll just use this thing. In collider physics, the problem is maybe you shoot in some protons at the Large Hadron Collider, and then there's an interaction. Actually, this thing happens to be a Higgs event. And the theory that we use is quantum field theory, quantum chromodynamics, there's electroweak theory. And that looks to be a very, very different problem from the problem of general relativity, where you have bound orbit of, let's say, two black holes, and they're emitting gravitational waves. But if you look at it the right way, in fact, these problems are very closely connected. And the reason is because of separation of scales. So for the black hole problem, as long as the black holes are widely separated and the wavelength of the radiation is long wavelength, then these black holes can be treated as point particles. If they're point particles, they're in our wheelhouse, and we can do calculations. This was understood a long time ago by many people. Iwasaki was one of the early ones. Then it was systematized by Goldberger and Rothstein, and there's been many, many papers on that. So just to be clear, I am talking about particle physics. So there's the Large Hadron Collider, ATLAS detector. I believe LBL is a part of the ATLAS collaboration. And we use our techniques, let's say Feynman diagrams, scattering amplitudes. So the scattering amplitude tells us about the probabilities of events happening at the Large Hadron Collider. Okay, and the thing that I'll be talking about is the application of the scattering amplitudes to the gravitational waves and gravity in general. So the two examples we have in our 2026 NERSC proposal, one is a kind of amusing. You probably heard Neil deGrasse Tyson and maybe Brian Greene tell you that gravity is inconsistent with quantum mechanics or something like that. And you may actually be wondering if that is a true statement. Well, we aim to use Perlmutter to answer that question. They say, but speak with great authority, but it's not that simple, really. Okay, so the one I'll be talking about right now, since it's a short talk, is just the idea of using quantum field theory methods for gravitational wave emission from binary black holes. In fact, the computer problems are almost the same. It's always the same issue. It's how do you do some integrals, Feynman loop integrals. That's standard in quantum field theory. And those loop integrals, they appear in both of these problems and also, of course, in collider physics. So the way people normally do general relativity, of course, you start with Einstein. There's Einstein's famous equation. And what that tells you is the relationship of energy and momentum to the curvature of space and time. And anyway, you can listen to Neil deGrasse Tyson explain all that. That's not how we do things. We start from someplace completely different. We start from an observation that Feynman made, which is that we can derive all of general relativity just from one concept, which is that there exists a massless spin-2 particle called a graviton. Once you know that, then you use the consistency conditions of quantum field theory, in fact, to derive all of general relativity. And this is actually a very powerful approach for a certain class of problems. The class of problems is perturbation theory, which is in fact exactly what we need for the problem of gravitational waves. We're interested in doing perturbation theory. Okay, what's the problem? Is to get the waveform. You have two black holes, they're inspiraling. We treat them as point particles. We use the concept of quantum field theory. And as long as these are widely separated, then we can use those ideas for this part of the waveform where they're widely separated. And then as they merge, then you need a different technique, a non-perturbative technique that's called numerical relativity. Numerical relativity is very much like numerical solutions of Maxwell's equation. You solve the partial differential equation numerically, and then there's other perturbative techniques. So you have to put all of this together in order to get accurate waveforms. And how well do we have to do? And the answer can be up from this plot. If you look at where we are today, this is LIGO. And what this plot represents, if you look down here, this is it's basically sensitivity. So in the future, in the 2030s, we will be about 100 times more sensitive. It's actually unbelievable. 100 times more sensitive on the detection, the precision and detection of gravitational waves. What does that mean for the theory? Well, it means 2 more orders of perturbation theory. Now, if you're wondering, what does two more orders of perturbation theory mean? Those of you who've done a little bit of perturbation theory, you probably have an idea that each order of perturbation theory, especially if you're talking about general relativity, is a hell of a lot more complicated than the last order. It's basically like climbing Mount Everest. Each new order of perturbation theory is a serious challenge, which is why I'm here. We need a supercomputer. Okay, and the way this works, just to be clear, there's many techniques that have to be used to get accurate waveforms. There's numerical relativity, so that you can use near the merger. The mass ratio between the black holes is small. Numerical relativity can be used, small separation. Post-Newtonian, that was invented by Einstein himself. The bending of starlight and so forth, that's post-Newtonian. We use something called post-Minkowskian. In particle physics, we just call that perturbation theory, and then there's various other techniques, and you have to put all of this together. So we're contributing to this approach. Okay. Now let me just show you what one of these things looks like. So this was our very first paper where we used these ideas. This was in 2019. We didn't need a supercomputer back then, and the reason is because we were at relatively low orders of perturbation theory compared to what our collider physics friends are doing. So we could just import directly their techniques off the shelf. The thing works. Okay, maybe you need a little bit more than a laptop, but pretty much there's no supercomputer, a tiny cluster. You'd be done with all the integrals in one day. And the types of answers that you get, these are analytic expressions. There's a potential. V is the potential, like a Newton's potential. Actually, Newton is hiding in here. Very hard to read because this thing is relativistically invariant, so it has all the velocity corrections. But if you carefully look in here, you'll find Newton. And then if you look a little further, you'll find Einstein's the first post-Newtonian would be hiding in these two terms. So this is Newton corrected by general relativity. That's what we're after. Okay, there's a two-particle Hamiltonian. Okay, so that was the early days. This is order G cubed. This is quite a lot of fun to do. There's some fun stories about that, but obviously I'm not going to tell you that in so little time. Now, how do we know that this stuff is good? And the answer is, of course, there's many comparisons. So this is a comparison against numerical relativity in the overlap region. Numerical relativity you can use to solve any problem if you're willing to spend enough money. So for certain specific cases, you spend a lot of money. You can get highly accurate waveforms that you can then compare. Basically, you look in an overlap region. You can then compare directly to other techniques. So it tells us how well we're doing. And the answer is it's really working very well. This includes a certain resummation that I'm not going to explain here. But the basic idea is these points represent numerical relativity. And then this blue line represents an example using what's called it's the fourth post-Minkowskian order. It's the fourth order of perturbation theory that's included in here. Okay, and this thing looks really good, but it ain't good enough. The only thing this tells us is we got to go on. We got to go on to the next order. Okay, and to get on to the next order, it's in some way it's very straightforward, but you encounter a serious bottleneck where the supercomputers come in. So the idea is the way we do these calculations is we start with the scattering amplitudes, and then there's a certain processing that you do, which is pretty straightforward, and you get an integrand which needs to be integrated, that then allows you to obtain physical observables or a two-body Hamiltonian that then can be used for data analysis. Now the hard step is right here. We have a bunch of integrals. I'll show you what some of these integrals look like. In principle, the computer codes that are used in collider physics by theorists making predictions with Feynman diagrams in collider physics, there's a program called FIRE that's used. In principle, you can apply it just here, except for the problem that these integrals are really hard. We're at a very high order. We're now pushing beyond where people in collider physics work. So we need to improve this greatly, and we have worked extremely hard to make the code very fast. I'd say we're running at least 1,000 times faster than anything you can get off the shelf. How exactly that's done is a fairly complicated story. And in fact, the advances we're making are going to feed back into collider physics because it's the same code. You can now use all the advances that we put. There's a new version out. I'm not an author of that, but the authors have modified things in order to help us make things go faster. So there'll be this feedback into collider physics. And we need the supercomputers to do these integrals. Okay, how do you do one of these integrals? So there's an integral, it looks something like this. There's a bunch of denominators, those are Feynman propagators, and there's some numerator. And the basic idea is you don't do the integral by doing an integral. No one ever does an integral by doing an integral. You do it by actually some completely different techniques. What you do is you set up a linear system of equations created by integration by parts. So you create a total derivative. That total derivative is 0. Whoops. And if you take that derivative and you actually carry it out, you get a spray of integrals. And that spray of integrals is an equation, a linear relationship between integrals. And then you need to solve that linear system. And then when you've solved that linear system in terms of what are called master integrals, you create differential equations, and then you solve the differential equations. That's the way to do these integrals. Okay, but the problem is it's right here. You have to solve very large linear systems, matrices, essentially 1 million by 1 million and beyond. But you have to do it analytically. Okay, and the question is how to go about doing that. Well, first let me show you what the integral looks like. So you can see this is not an integral you want to meet in a dark alley. Unhappy. Actually, to make matters worse, it's not just one integral, it's millions of them. And then even worse, when you start doing the integration by parts, it explodes even more. So the thing grows out of hand, completely out of hand, and you're trying to do this analytically. So the integrals we have, they turn out to be a function of 2 variables. And those 2 variables, we have to have the exact analytic answer. Now you'd think that a supercomputer is not good for this because you're trying to do something analytically. But in fact, there's a magical way of doing this. It's the idea of finite fields. If you haven't seen this before, it's really cool. So suppose you have a very large linear system. Doesn't matter exactly what it is. And it has millions of unknowns. It's some giant system. And the solution that you're looking for is a rational function of some kind. It's a rational function of some variables. Maybe some kinematic variables. And the question is, how do you solve this analytically? And the answer to that is you don't solve it analytically, you solve it numerically, but you have to do it in a very special way. Obviously, you can't use floating point because then you can't reconstruct the exact answer. What you do is you use finite fields. You use arithmetic over a prime field. So you pick a point, a numerical point, you evaluate the system and solve the system on that one prime, on that one point. And then you keep on doing this over and over and over again. Lots and lots of points, you solve the system. And then you use multiple prime fields. And then the Chinese remainder theorem says that you can always analytically reconstruct this thing. And the only thing that you need to do is have enough primes and the reconstruction is possible. This is something that's bread and butter in collider physics. This is how all high order calculations are done using finite fields. So we, of course, just import that and, of course, have polished the code to make it really fast and efficient. We need about 10,000 points per reconstruction. There's 300 types of integrals. Each type can have millions of integrals, actual integrals. And so you throw 10,000 points and you solve for one type, then you go on to the next one and so on. The parallelization is trivial. We use MPI, but only to bundle the jobs so that we can age the jobs properly on Perlmutter and get it through the queue as fast as possible. Well, I'm telling you, I'm giving away some secrets I see, but anyway, we use MPI for that, but the parallelization is completely trivial. Once you have all the points, then you run the Chinese remainder theorem and do the analytic reconstruction. Actually, one question I have for the experts, if there's some way we can use GPUs to help us with this. Oh, here, let me show you how we've been using this. So we got our first time, it was on July 14th, we got the email, you have time. Okay, we got time within a day, we're trying stuff. You can see there's this long lead time because every supercomputer has its issues. Then at some point you can see we start doing our first production run right here. And then you see it's doing kind of measly. We're not doing very well. But luckily the consultants are great. I write to them in 4 hours, I get the answer. And then it was clear what we needed to do. Turn on MPI, bundle the jobs. And then you can see we're screaming along at 4,000. This is 4,000 node hours a day is what we were averaging, which means that we used up all our time in about 10 days. So anyway, obviously we need some more. If we had another 100K hours, we'd be starting to run tomorrow. We'd use 50K in another 2 weeks. Anyway, it's really been awesome. Okay, and so what's the summary? So the supercomputers, they're really crucial now in quantum field theory as we're pushing to high orders of perturbation theory. We need those supercomputers. It fits perfectly with the finite field methods for solving the integrals. And this is a very standard technique. And these methods, these finite field methods and integration by parts techniques, they're completely standard in collider physics, and now we're carrying it over to gravity in order to push the perturbation theory as far as we can go. And we're aiming for another 2 orders of perturbation theory. We're working on the first order right now. And I think in the coming years, we expect to crucially rely on NERSC for computer support. Thank you.
Questions?
How do you validate all the results that you're producing?
Well, we do what's called post-Minkowski, there's an overlap with post-Newtonian. So basically, if we take our expression and we series expand in velocity, we can compare. So this of course is a very important question because you're probably thinking, who's this crazy guy coming in with all this thing, you do it in this funny way, and then you're supposed to get Einstein, and then you actually get the right answer. How do you know that? Indeed, there's quite a bit of fun, and we pour a lot of effort into exactly that question to validate. So certain things get validated very quickly. So when you do the analytic reconstruction, it will not reconstruct if you've made even one error in one point. Then there's going to be a problem with reconstructing. But the real question is, how do we actually know that we get general relativity? Well, let's just say it was quite a bit of fun to convince the general relativists that we're actually doing it correctly. And let's just say that they were so sure that we were wrong that they would calculate really hard. And after a lot of calculation, they confirmed us, so we know it's correct. So they accept our results and the methods as being correct. But we continue, of course, to worry about that question of validation.
Kind of a funny question. You're working with like particle physics methods and general relativity. What metric signature? Do you ever run into like which metric signature people use? Because I know there's like a contention.
No, we use West Coast. We use particle physics, so it makes it very hard to compare our results to the general relativity community because endless numbers of minus signs. But we're particle physicists. I'm too old to change my metric.
Okay, awesome. Thank you so much. That was great. Thanks.